So namaskar, adab, sat shri akal, 𝐂𝐤𝐬𝐞, 𝐂𝐸𝐴𝐻𝑒𝐿𝑂 and welcome in GATE Wallah. So student, in this lecture we will discuss longitudinal, transverse and torsional vibration of single degree of freedom system. Okay. So and today our single degree of freedom part will get complete. Na? In today's lecture I am going to discuss longitudinal, transverse and torsional vibration of single degree of freedom system. So I am starting. So first of all, we'll discuss its introduction, that is what is longitudinal, transverse and torsional vibration. Then we'll discuss one by one. First we'll discuss longitudinal vibration of single degree of freedom system and how we can calculate natural frequency of longitudinal vibration. Then we'll discuss same thing for transverse vibration and then we'll discuss this for torsional vibration. Okay, so without any delay, I'm starting. First of all, what is the meaning of longitudinal, transverse and a torsional vibration? Suppose this is a shaft or beam or bar, whatever you want to refer, you can refer. Okay. And in this shaft, here I have attached a point mass. Okay. Suppose this mass of the rotor, this I am referring as rotor, is M. Okay. Now we know whether it is shaft, whether it is beam, whether it is bar, the axis which is along length, this axis is known as transverse axis. And the axis which is along the cross section, along the cross section, see in this structure, this is known as cross section. And the axis which is along cross section is known as transverse axis. Now see, what is the meaning of longitudinal vibration? So suppose I am disturbing this mass from its mean position. Right now this is its mean position. Now suppose I am disturbing this mass from its mean position in longitudinal direction like this. Okay. And after that I am releasing that. Okay. Now see, if you will disturb the mass from its mean position like this, can I say this bar will deform in longitudinal direction? Means axial deformation will occur in the bar. So what will happen now? In that case, restoration will occur due to the axial stiffness of the bar. Okay, because if you will disturb the mass in longitudinal direction like this, so this bar will elongate. And since this bar is elongating, means deflecting in axial direction, so axial stiffness of the bar will, axial stiffness of this structure will provide restoration. Now what will happen? Now whatever force I have applied in this mass to disturb this, if I will release that force, so due to the axial stiffness of the bar, this rotor will try to come back to its mean position. But again, when it will reach to its mean position, it will have some velocity. And due to that velocity, and direction of velocity will be towards this side. Due to this velocity, this rotor will go in this direction. Okay. And again, if rotor is going in this direction, means again it is disturbing from mean position. So again here axial stiffness will come into picture. So what will happen now? This rotor will vibrate like this. And the vibration which is occurring, it is occurring in longitudinal direction. So this vibration is known as longitudinal vibration. Like in spring mass system, vibrations occurs now. Okay. Same way here also vibration is occurring. Here restoration is provided by the stiffness of this spring. Similarly, here restoration is provided by the longitudinal axial stiffness of this bar. Okay. And this vibration is known as longitudinal vibration. Longitudinal vibration means vibration will occur along longitudinal direction. And in this case, axial stiffness of the bar, this is very important line, is responsible for restoration. Okay. Now what is transverse vibration? Now in the same structure, suppose instead of disturbing this mass from its mean position in longitudinal direction, suppose I am disturbing this mass from its mean position in transverse direction. Okay. Suppose I am applying a impulse for short duration and I am disturbing this in transverse direction. So what will happen? If you disturb this in transverse direction, this shaft will bend like this. Just try to understand. This shaft will bend like this. Okay. And since shaft is bending, here bending stiffness of this shaft, whether you are referring this as shaft, beam and bar, it is your will. Okay, but the bending stiffness of this structure will provide restoration. Now what will happen? Whatever force I have applied to disturb this mass, if I will release that force, so due to the bending stiffness of this structure, it will try to come back to its mean position. But when it will reach to its mean position, it will have some velocity and direction of velocity will be upward. So due to that velocity, now this rotor will go in upward direction, it will go in downward direction, again this structure will bend. So what will happen? Ultimately it will bend like this. It will vibrate like this, like this, like this, like this. And when it is vibrating like this, here vibration is occurring in transverse direction. And this vibration is known as transverse vibration. Now again in transverse vibration also restoration is occurring due to stiffness. But now that stiffness is not axial stiffness, that stiffness is bending stiffness. So we can say in transverse vibration, restoration occurs due to bending stiffness of the structure. Okay. Next, what about torsional vibration? So see, now what I am doing, instead of disturbing the mass like this or like this, what I am doing, by applying a impulse torque about longitudinal axis, I am rotating this rotor like this. Okay. Okay, I am rotating the rotor like this. Just try to imagine. Means I am rotating about transverse. I am rotating about longitudinal axis. Now, what will happen when I will try to rotate the rotor like this? Now, can I say this shaft, this point of the shaft will twist? Why? Because now this end of the shaft is fixed. So in this shaft, rigid body rotation cannot occur, because suppose if this point is A, this point is B. So A cannot rotate, but B will rotate due to the rotation of rotor. So what will happen when B is rotating, means it will rotate about A. So that's why twist will create in the shaft. So can I say if we will disturb the rotor like this, twist will create in the shaft. Suppose this and B, it will twist will create at B like this. And due to that twist, here torsional stiffness will come into picture, and that torsional stiffness will provide a restoration. How to calculate torsional stiffness, that we'll discuss later, don't worry. But here torsional stiffness will provide restoration. Now what will happen, that impulse torque which we applied in the rotor to rotate this or to disturb this from mean position, if I will remove that torque, so due to the torsional stiffness, it will try to come back to its mean position. But when it will reach to mean position, it will have some velocity. Since right now it is rotating, so it will have some angular velocity. And due to that, now it will disturb in this direction and it will vibrate like this. So here if you see the vibration now, vibration will occur about longitudinal axis. And this vibration is known as torsional vibration. And in torsional vibration, restoration will occur due to the torsional stiffness of this shaft. Okay. So whenever this type of question is coming, examiner will mention whether you have to calculate longitudinal natural frequency of longitudinal vibration or transverse vibration or torsional vibration. Because how only by looking the diagram you can tell what examiner wants. So he will mention, don't worry. Okay. Or by looking the question you will be able to judge what examiner wants to ask. But generally it should be mentioned. So if I am disturbing the rotor like this in longitudinal direction, then releasing the force which I am applying to disturb this, it will vibrate like this. This vibration is known as longitudinal vibration. In longitudinal vibration, axial stiffness of this structure is responsible for restoration. If I am disturbing this mass in transverse direction, then it will bend. So in this case, vibration will occur in transverse vibration, and in this vibration, this is known as transverse vibration. In this case, bending stiffness is responsible for restoration. If I am disturbing the rotor like this, then releasing the torque, then it will vibrate like this. Means it will vibrate about longitudinal axis, and this vibration is known as torsional vibration. And in torsional vibration, torsional stiffness of the shaft is responsible for restoration. Okay. Now we'll discuss one by one. So first I am discussing about longitudinal vibration. Okay. So now I am discussing longitudinal vibration. So now whatever diagram I am making, now I will not repeat again and again. Here longitudinal vibration is occurring, because now my heading is longitudinal vibration. So whichever case I am discussing, in that case I want to calculate natural frequency of longitudinal vibration. And I already discussed, in longitudinal vibration, axial stiffness is responsible for restoration. Okay. Now first I am taking very simple case to understand this. Okay. Okay. Suppose this is the shaft, beam, bar, whatever you want to refer. Generally in longitudinal vibration, I refer this as bar. Okay. Suppose the mass of this rotor is m. So here one point mass is attached, which I am referring as rotor, whose mass is m. Okay. But here we are referring this beam is having negligible mass. or this bar is having negligible mass. Reason? Because right now we are discussing vibration of single degree of freedom system. Okay, because if the mass of bar is given, it is distributed mass, na? So its degree of freedom will be infinite. Okay, that we are not discussing today. Yes. Okay, because right, first we'll complete single degree of freedom discussion. Then in next class I will start 2 degree of freedom, and in last class I will discuss continuous vibration. And in continuous vibration we'll discuss when the mass of this bar is given, because that will have infinite degree of freedom. But today we are only discussing vibration of single degree of freedom system. So in single degree of freedom system only one point mass will be involved, and mass of other part will be negligible. So here mass of bar is negligible, and here this rotor is involved whose mass is m, and it is a point mass. Okay. Now suppose the length of this bar is L. Okay. Now here cross sectional area of the bar is suppose A, it is cross sectional area, and Young modulus of this bar is E. Young modulus is the material property. Okay. Here now, to understand the concept of longitudinal, transverse and torsional vibration, you should know the concept of strength of material subject also. Okay, like if any bar, in any bar axial load is acting, so how you can calculate deflection of the bar. If in any bar torsional load is acting, so how you can calculate angle of twist. If in any bar transverse load is acting, so how we can calculate deflection of any point. Okay, here I will write the formula, but this thing you will study in strength of material. Okay, the formula are simple. Now see, Young modulus of this bar is E. This will be given in the question. Sometime now, to save your calculation work, examiner directly gives the product of A and E. What is A? It is cross section area. What is E? It is the Young modulus of the material. Okay, and the product of A and E is known as axial rigidity. Okay. Now, see, we want to calculate natural frequency of transverse vibration. So now what we'll do? Okay, here I have already discussed that restoration will occur due to the axial stiffness. Okay, so can I say if I want to calculate the natural frequency of this vibration, and if I will use equivalent stiffness method, why I can use equivalent stiffness method? See, when I was discussing equivalent stiffness method, I have clearly mentioned that method we will use. In equivalent stiffness method, the formula to calculate natural frequency was root over K equivalent divided by the value of point mass m. And if you are using this formula, but when this formula is valid, first condition, in that system only one point mass should be involved. So right now only one point mass is involved. Good. And second, restoration should occur only due to stiffness. So here restoration is occurring due to the stiffness of bar, and that stiffness is known as axial stiffness. So ultimately here restoration is occurring due to stiffness, that stiffness is axial stiffness. So this formula is valid. Okay. So here we need to calculate K equivalent only. Okay, and here this K equivalent is also known as axial stiffness of this bar. How we can calculate K equivalent? So what is the method to calculate K equivalent? What we'll do, at this location where point mass is attached, to calculate axial stiffness. Suppose I am drawing this diagram separately. Here I am drawing this diagram only to calculate axial stiffness. Okay. In exam you need not to draw separate diagram. Just for explanation I am drawing separate diagram. Now point mass is attached here. Now at this point what we will do, we will apply a concentrated force in axial direction. Okay, why I am applying in axial direction? Because in this method what we do now, at the point where mass is attached, we apply a static force in the direction of vibration. So right now longitudinal vibration is occurring. In longitudinal vibration means vibration will occur in axial direction. That's why at this point we'll apply a static force in axial direction. Suppose that force I am representing as P. Okay. Then we'll calculate the deflection of the same point in the axial direction. So suppose deflection of this point I am representing as delta. So can I say P by delta will be the stiffness of this bar, and this stiffness which I am referring as K equivalent is also known as axial stiffness. If you want you can simply refer this as K also. So what is K? At the point where rotor is attached, if you want to calculate natural frequency of longitudinal vibration, apply a static force P in longitudinal direction. Then due to this point P, load P, calculate the deflection of same point in this direction. Suppose that is delta, then P by delta will be the equivalent stiffness of this system. This is also known as axial stiffness of this bar. Okay. Now this formula we have already studied. Suppose this point is A, this point is B. My objective is to calculate the deflection of point A, that is delta A. Now if you want to calculate deflection of any total deflection of any point, we will calculate deflection of that point with respect to fixed point, because deflection of fixed point is always 0. So delta AB is nothing but delta A, because delta B is 0. Now how we can calculate delta AB? So you can see in AB portion axial load is acting, which is P. Now cross section area of each cross section of AB is A. Right now area is same and Young modulus is E. Now this formula we have studied in strength of material. If in any portion of the bar axial load is acting, which is P, and if area and Young modulus of that portion is constant, then formula to calculate change in length of that portion is PL upon AE, where P is the axial force of each cross section of the bar, A is area, E is Young modulus. So right now since axial force of AB portion is same, which is equal to P, area is same, E is same. So can I say axial change in length of AB portion will be PL upon E. Okay. And since B is fixed, it is also total displacement of point A, which I am referring as delta. So from this expression, if you calculate P by delta, it is coming AE by L. I think you have studied this formula in strength of material also. Okay. Now we will remember this formula, because I will not do this discussion again. Okay. So can I say the axial stiffness of the bar, whose one end is fixed and at other end rotor is attached, because here rotor was attached. That's why I applied load P at this location. And if axial rigidity of that portion is same, axial rigidity is same means area is same, Young modulus is same, then direct formula to calculate axial stiffness of that portion of bar is AE by L. Now we'll remember this formula, where A is cross section area, E is Young modulus, L is length. Okay, I will suggest always use SI unit to calculate this stiffness. Okay, or if directly AE is given, so A is the product of A and E, that is A is known as axial rigidity of this bar. Okay. Okay. Now if we calculated, or if you know this formula, so now if same question is coming in the exam, how you can draw the equivalent diagram to solve the problem? Now see, whenever this question is coming, see this end is fixed, here rotor is attached, and AE of this entire bar is same, and we know the formula to calculate axial stiffness of this portion. This is AE by L. So what you can do now, draw its equivalent diagram whenever you want to calculate natural frequency. And equivalent diagram, what we'll do, we'll replace this bar by a spring. Okay, and suppose, and what will be the stiffness of that spring? Stiffness of this spring is nothing but axial stiffness of this bar, and axial stiffness of this bar is AE by L. Okay, now with this spring will attach this mass M. Now we know what is the formula to calculate natural frequency of this system, root over K by M. Now you can use same formula. So omega and natural frequency in radian per second, it will be root K by M. K is axial stiffness, which is AE by L. So it will be root over AE by L divided by M. If numerical is coming, area, E, length is given, so separately calculate K, just put value here. So this is natural frequency in radian per second. Understood? So if you draw equivalent diagram like this, na, the problem will become easy. Only you have to remember, if one end is fixed, at other end rotor is attached, then formula to calculate axial stiffness of this portion of bar is AE by L. From where I got this formula? That I had derived. Clear? Okay, now what is the benefit now? Right now axial rigidity is same for entire bar, but even if it is changing now suddenly, then also you will be able to easily calculate equivalent stiffness. How? Now I am drawing some more diagram. Suppose this question is coming. Suppose axial rigidity of this portion is A1 E1, length is L1. This portion is A2 E2, length is L2. Yes, and here rotor is attached. The mass of the rotor is M, and our objective is to calculate natural frequency of longitudinal vibration for this diagram. So simply draw equivalent diagram. What we'll do now, since axial rigidity of this portion is different, so I am considering, suppose this as bar 1. This portion is different, so I am considering this as bar 2. And beside this, this rotor is attached. So how will draw equivalent diagram? In equivalent diagram, first I will replace this bar 1 with spring 1, whose stiffness is K1, and K1 is nothing but axial stiffness of bar 1, which will be axial rigidity, which is A1 E1 upon length, which is L1. Now with this bar 2 is attached, So now with this spring will attach spring 2, which stiffness is K2, and K2 is nothing but axial stiffness of this portion of the bar, which will be A2 E2 upon L2. Now with this rotor is attached. So here attach the rotor. Rotor means point mass M. Okay. Now from this equivalent diagram, we can easily calculate overall K is equivalent stiffness. How? Suppose this is spring 1, this is spring 2. And you can see here spring 1 and 2 are making end-to-end connection. And we know end-to-end connection means they are arranged in series. So now we can say spring 1 and 2 are arranged in series. And what is the formula to calculate equivalent stiffness in series arrangement? We'll use reciprocal formula. Reciprocal means suppose their equivalent is K equivalent, because after that no other spring are left. So 1 upon K equivalent will be equal to 1 upon K1. K1 is, or first I am writing K1 plus 1 upon K2. Now in numerical you can do the calculation. I am just explaining how to calculate K equivalent. Now after that, you know, you have to only do the calculation. 1 upon K1, and K1 is A1 E1 upon L1. L1 will go above, plus 1 upon K2. K2 is A2 E2 upon L2. L2 will go above. So now after that all are calculation. Na? It will be, if you take LCM, it will be A1 E1 A2 E2. Now this divided by A1 E1 is A2 E2 into L1. So it will be A2 E2 L1 plus A1 E1 L2. Okay. So K equivalent will be A1 E1 A2 E2 upon A2 E2 L1 plus A1 E1 L2. You can do the calculation. Okay. And after calculating K equivalent, now we can calculate natural frequency of longitudinal vibration. It will be root over K equivalent divided by the value of rotor mass M, and K equivalent is A1 E1 A2 E2 upon A2 E2 L1 plus A1 E1 L2 into the mass M. Okay. But this calculation you can do na. I was just explaining this concept. Clear? Like suppose if diagram is given like this. Here rotor is attached na. Suppose the mass of the rotor is M, axial rigidity of this portion is A1 E1, this length is L1, axial rigidity of this portion is A2 E2, this length is L2. Okay. So now how we can draw equivalent diagram? So see, whenever rotor is attached at the middle na, so always we'll calculate this side portion separately and this side portion is separately. Right now the axial rigidity of both this bar and this bar is different, but even if axial rigidity of this bar and this bar are given same, then also we'll consider this bar separately and this bar separately, because rotor is attached at the middle. Okay, because now if you try to recall spring arrangement, just try to recall, if mass is placed at the middle now, we know the equivalent stiffness of this side system and this side system will be in parallel to each other. Same concept will come here na, because rotor is attached at the middle. So this side portion equivalent and this side portion will be equivalent, will be in parallel arrangement. Okay. But how they are in parallel now, when you will draw equivalent diagram as a spring, you will easily understood. Right now only remember, if rotor is placed at the middle, always will consider this side portion of the bar and this side portion of the bar separately. So suppose this is bar 1, okay, this is bar 2. Now how will draw equivalent diagram? So first I am replacing bar 1 by spring 1, whose axial stiffness is K1, and it will be axial rigidity of this portion is A1 E1, length is L1. So it will be A1 E1 upon L1. Now with this rotor is attached. So now first attach the rotor, whose mass is M. Okay. Now after that, this side, this bar 2 is attached, whose suppose axial stiffness is K2. And how we can calculate K2? Axial rigidity of this portion is A2 E2 and length is L2. So it is A2 E2 upon L2. That's it. Yes. Now after drawing this equivalent diagram, now we can calculate overall K equivalent. How? Suppose this is spring 1, this is spring 2. So you can see spring 1 and 2 are in parallel. So here spring 1 and 2 are in parallel. So now we can calculate K equivalent. Okay, in parallel, suppose their equivalent stiffness is K equivalent. So for calculate K equivalent in parallel arrangement, just add the stiffness of individual spring, you will get overall K equivalent. So you will calculate K1 plus K2. Now after that it is calculation. K1 is A1 E1 upon L1 plus K2 is A2 E2 upon L2. So it will be LCM is L1 L2. L1 get cancel, here L2 will remain. So it will be L2 into A1 E1 into L2 plus here L2 will get cancelled. So L1 will multiply with this. So it will be A2 E2. So this is K equivalent. And after calculate K equivalent, we can calculate natural frequency of longitudinal vibration. It will be root over K equivalent upon the mass of the rotor, which is M. Now K equivalent is A1 E1 L2 plus A2 E2 L1 upon L1 L2 into mass. Clear? So like this you can solve the problem of longitudinal vibration. I am discussing some questions also, like this question. In this question we have to find the expression of natural frequency of longitudinal vibration in radian per second. Means ultimately our objective is to calculate omega n. Okay, very easily you can calculate. So suppose here I am discussing the solution. See, axial rigidity of each segment is given in the diagram, na? So now, how first we'll draw its equivalent diagram. How? Suppose this is bar 1. With this bar is attached, its axial rigidity is different, so I will consider separately. So it is bar 2. Now here rotor is attached. Whenever rotor is attached, so we will always consider this side portion separately. So that's why I will consider this bar separately. Suppose this is bar 3. Yes. Now draw the equivalent diagram. What we'll do, we'll replace bar 1 by spring 1, whose axial stiffness is K1. And how we'll calculate K1? Axial rigidity of bar 1 is 2AE. So above said axial rigidity divided by length. Length of bar 1 is 2L. Now 2 will get cancelled. So it will come AE by L. Calculation you can do. Okay. Now with this bar 1, this bar 2 is attached. So we'll replace bar 2 by spring 2, whose axial stiffness is K2. Now I will calculate K2. So axial rigidity of bar 2 is AE divided by length of bar 2 is L. Now with this rotor is attached. So first we'll replace this by point mass M. Now after that this side bar 3 is attached. So we'll replace bar 3 by spring 3, whose axial stiffness is K3. And how we'll calculate K3? So axial rigidity of this portion is 2AE upon length is L. Yes. So this is equivalent diagram. Very good, Akash. Okay. Now prepare sincerely for GATE exam. Na? Now, see. This is spring 1, this is spring 2, this is spring 3. Now from this diagram we have to calculate equivalent stiffness. And how we can calculate equivalent stiffness? So we know whenever mass is placed at the middle, this side system equivalent and this side system equivalent will be in parallel to each other. So first of all we need to calculate equivalent stiffness of each side. So this side only one spring is coming. So we know equivalent stiffness of this side, this is K3. But now we will calculate equivalent stiffness of this side, and this side 2 spring are attached, na? 1 and 2. And you can see this 1 and 2 are having end-to-end connection, and end-to-end connection means they are in series. So if we want to calculate equivalent stiffness of 1 and 2, suppose that I am referring as K12. So how we can calculate K12? So since 1 and 2 are in series because they are having end-to-end connection, so here 1 and 2 are in series. And in series arrangement to calculate equivalent stiffness we use reciprocal formula. So how we can calculate K12? 1 upon K12 will be equal to 1 upon K1 plus 1 upon K2. So 1 upon K12 is equal to 1 upon K1. K1 is AE by L. L will go above side plus 1 upon K2. K2 is also AE by L. So 1 upon K12 it will be equal to AE is LCM. Here it will be, or you can directly write now L upon AE plus L upon AE is coming. So it will be 2L upon AE. Okay. So K12 is reciprocal is this. So it will be AE by 2L. Okay. So now we know the equivalent stiffness of this side system, which is K12, and equivalent stiffness of this side is K3. And we know equivalent stiffness of this side, that is K12, and equivalent stiffness of this side, that is K3, are in parallel arrangement. So now I can calculate overall K equivalent. Reason? Because now we know K12 and K3 are in parallel. So I can calculate their equivalent, and their equivalent means overall K equivalent, because after that no other spring are left. And okay, so overall K equivalent now I can calculate. And we know in parallel arrangement, to calculate equivalent stiffness, we add the stiffness of individual part. So K equivalent will be K12 plus K3. Now K12 is AE by 12 plus K3 is 2AE by L. Okay. So K equivalent AE by L I am taking common. So it will be 1 by 2 plus 2. How much it is coming? 2 2 is 4 plus 1. 5 divided by 2. So K equivalent is coming 5 AE by 12. You can check the calculation. Yes. So now you got to know the overall equivalent stiffness of this system. So now we can calculate natural frequency of this longitudinal vibration in radian per second. It will be square root of K equivalent upon the mass of the rotor, which is m. Now root over K equivalent is 5 AE upon 2L. Okay. So this is the expression of natural frequency of this transverse vibration. Sorry, longitudinal vibration in radian per second. That's it. If examiner is asking in hertz, it will be omega n by 2 pi. If examiner asking time period, it will be 2 pi by omega n. Very easy. Okay. Now one more question I am discussing. This question. Okay. Here we have to calculate natural frequency in hertz. So first we'll calculate in radian per second, then we can convert that in hertz. Na? Okay. So I am drawing first this diagram separately. Here we have to calculate natural frequency, but here it is not mentioned that in this bar longitudinal vibration is occurring. Reason because that I can tell by observation. See, here point mass is attached here and spring is vertical. So definitely, if it is not mentioned, this point mass will vibrate in vertical direction. Okay. Now, if this point mass will vibrate in vertical direction, simply vibration will occur in the spring. But just try to understand, when vibration will occur in the bar, this point of the bar will move like this. Means it is moving in longitudinal direction. So in this bar also longitudinal vibration will occur. And since longitudinal vibration will occur, so when I will consider the stiffness of this bar, I will take axial stiffness of the bar, because in bar longitudinal vibration is occurring. So now what we'll do? Now we'll draw the equivalent diagram. Okay. See how we'll draw. First we'll replace, because longitudinal vibration is occurring. So first we'll replace this bar. Suppose this bar is 1. It is already a spring. Suppose this spring I am referring as 2. So what we'll do? We'll replace this bar 1 by spring 1, whose stiffness is K1, and this is nothing but axial stiffness of this bar. And how we can calculate axial stiffness? So right now cross section area of the bar is given. Suppose that I am referring as A. But remember, whenever you are doing calculation, I use SI unit. Because when you are calculating stiffness, I will suggest calculate in Newton per meter. So that's why I am saying use SI unit. So right now I am denoting the area of the bar as A, Young modulus is E, and suppose length of this bar 1 is L. Okay, I will put the value later. So axial stiffness will be AE by L. I will calculate the value, don't worry. Okay, so this is the axial stiffness of this bar, which I am referring as K1. Now below this bar, now this spring is attached, whose stiffness is K, it is given in the question. So now this spring is attached, which I am referring as K, referring as spring 2, whose stiffness is K. It is already given. It is 20 mega Newton per meter. In Newton per meter, it will be 1 mega Newton is 10 to the power 6. So 20 into 10 to the 6 Newton per meter. Now below this mass is attached, M, and the value of M is 40 kg. So this is the equivalent diagram. This is spring 1. Now you can calculate K equivalent also, because 1 and 2 are in series. But before that, first calculate the value of K1, because K2 I know with value. Okay, so now we can calculate K1. K1 is AE by L. Now A is cross section area of the bar. It is 100 mm square. Convert this in meter square, because I am using SI unit. So see, 1 mm is 10 to the power minus 3 meter. Now its square is coming. So 1 mm square is 10 to the power minus 6 meter square. Now similarly, E is given in gigapascal. Convert this in SI unit, means in Pascal. Okay. Now 1 gigapascal, you should know 1 giga means 10 to the power 9. So 1 gigapascal is nothing but it is 10 to the power 9 Pascal. So it will be 200 into 10 to the power 9 Pascal. Next, length is already we know in SI unit, because it is given in meter. So can I say K1 will be A, which is 100 into 10 to the minus 6 into E, it is 200 into 10 to the 9 upon length, which is 1 meter. So from this I can calculate K1. How much it is coming? Okay. And since we know na this stiffness in 10 to the power 6 order, so I will suggest calculate this also in 10 to the power 6 order. So it will be easy for calculation. 100 into 10 minus 6. So we are calculating this in 10 to the 6 order. It is coming 20 into 10 to the 6 Newton per meter. Yes. So this is K1. Okay. Now we can calculate overall K equivalent. How? We know this K1, that is spring 1, and K, or you can refer as K2, that is spring 2, are in series arrangement because they are having end-to-end connection. So we can calculate overall K equivalent because 1 and 2 are in series. Okay. And now suppose they are equivalent, I am referring as K equivalent because after that no other spring are left. And in series arrangement, we use reciprocal formula to calculate equivalent stiffness. So 1 upon K equivalent will be equal to 1 upon K1 plus 1 upon K2. K2 means K because stiffness of this spring is K. Now just put the value 1 upon K equivalent equal to 1 upon K1. K1 is 20 into the 6 plus 1 upon this K is also 20 into the 6. So how much K equivalent is coming? Okay, it will come 10 into 10 to the 6 Newton per meter. You can check the calculation. Okay. Now after calculating K equivalent, we can calculate its natural frequency in radian percent, that is omega, and omega n will be root over Ke by the value of point mass m, root over Ke. Ke is 10 into 10 to the 6 upon the value of point mass m is 40 kg. So how much omega n is coming? Root over 10 into 10 to the 6 divided by 40. It is coming 500, but it is coming in radian per second. Okay. So natural frequency of this vibration in radian per second is 500 radian per second. But examiner is asking in hertz. Now we know, if we know natural frequency in radian per second, we can convert that in hertz. What is the formula? The natural frequency in hertz, that is Fn, will be omega n divided by 2 pi, where omega n is natural frequency in radian per second. Right now omega n is 500 divided by 2 pi, this much of hertz. So how much natural frequency in hertz will come? It will be 500 divided by 2 divided by pi. It is coming 79.577 hertz. Okay. So this is the value of natural frequency of this vibration in hertz. It is coming 79.577. So for this question, the correct answer is 79.57. Okay. Okay. So we have completed the longitudinal vibration of single degree of freedom system. Okay. Now we'll discuss transverse vibration of single degree of freedom system. Okay. Now here you should know the formula, how to calculate deflection of any point due to load, transverse load in the beam, because that formula you will study in strength of material. I will directly write the formula only here. Okay. Now suppose this is the beam. Okay. Now you can refer this as beam, bar, shaft as per your will, but generally when transverse vibration occurs in any structure, generally we refer that structure as beam. Okay. Now in this beam or in this structure, at the free end, suppose a point mass m is attached. Length of this beam is L. Here the flexure rigidity, like in axial longitudinal vibration, axial rigidity is important. In transverse vibration, flexure rigidity is important. Why? How? You will understand. Don't worry. So suppose the flexure rigidity of this beam is EI. What is E? E is again Young modulus. What is I? I is area moment of inertia. It's not mass moment of inertia, it's area moment of inertia of cross section about neutral axis. This thing you will study in strength of material. Okay. C. And the product of E and I is known as flexure rigidity. So sometime now, to reduce calculation work, examiner direct gives the value of flexure rigidity, which is the product of E and I. Now see why this EI is required, you will understand, don't worry. But see, here we are discussing transverse vibration. Transverse vibration means in this structure, transverse vibration is occurring. Transverse vibration means, now what we'll do, we'll disturb this mass from its mean position is transverse direction. Okay. So due to that, what will happen? This beam will bend. Now after that, whatever force I have applied to disturb this mass, if you will remove that force, so it will vibrate like this. And this vibration is known as transverse vibration. And in transverse vibration, restoration occurs due to the bending stiffness of this beam. Okay. Now again, if I want to calculate natural frequency of transverse vibration in this case, again I can use equivalent stiffness method. So in this, because in this structure also only one point mass is involved, which is m, because beam is massless. And second, restoration is occurring only due to stiffness. But now that stiffness is not axial stiffness, that stiffness is bending stiffness. Reason? Because during vibration, this structure is bending. So what will happen? If stiffness of the system is K, mass is m, the formula to calculate omega n is root K by m. So again, I will use same formula root K by m, but here K is nothing but bending stiffness of this beam. So suppose bending stiffness I am denoting as KB, B for bending. So suppose bending stiffness this beam is KB. Okay. Bending stiffness means I am replacing this structure with single spring. Below this I am attaching the mass. And the stiffness of that spring is nothing but bending stiffness of the beam. Okay. But here how will calculate bending stiffness? How will calculate bending stiffness? Just I am explaining. But at last you have to remember the formula in your mind. See. What we'll do for bending stiffness calculation. And now my objective is to calculate KB calculation. This is the beam whose flexure rigidity is EI, length is L. Okay. Now at the location, what is the formula to calculate bending stiffness? At the location where concentrated mass is attached. Here it is attached, right now it is attached the free end. At that location we will apply a concentrated load in the direction of vibration. And since right now we are discussing transverse vibration, means can I say right now vibration is occurring in transverse direction? And since vibration is occurring in transverse direction, at this point where mass is attached, we will apply a static load P. You can refer this load as F also. But here na, in strength of material, generally we are more familiar with P naming. That's why I am using P. So at this point we will apply transverse load P, concentrated load P in transverse direction. Why I am applying in transverse direction? Because transverse vibration is occurring. And now due to this load P, I will calculate the deflection of the same point in transverse direction. Suppose that deflection is delta. Then P by delta is the stiffness of this beam, and that stiffness is bending stiffness because we have applied P in transverse direction. So this will be the bending stiffness. Now from this formula to calculate K find the expression of KB, you should know the formula of delta. And this we have studied in strength of material. It is a cantilever beam. Whenever one end of the beam is fixed, other end is free. That is cantilever beam. And in cantilever beam, you have studied this formula in strength of material. Whenever load P is applied at the free end, and if we are calculating the deflection of the same point, the formula to calculate deflection of same point due to transverse load P is PL cube by 3I. This formula you have studied in strength of material. And okay, that we have to remember. Even in strength of material, we discuss various methods to calculate this formula. Okay, but even when we are discussing various method now, then also in strength of material also we remember this formula, because in deflection of beam chapter for some standard case we remember the formula to calculate deflection. Okay, and in vibration now generally question will come from standard case. So this formula already we have remembered in strength of material. So right now just mark this formula in your mind. Then whenever in cantilever beam concentrated load P is applied in free end, so formula to calculate deflection of the same point is PL cube by 3I. Okay, and this formula should be fit in your mind. Now if you know this formula, you can easily write the expression of KB, because KB is nothing but P by delta. And if from this you will calculate P by delta, it will be 3I upon L cube. Now this you can do in your mind. If in cantilever beam concentrated load is acting at free end, the formula to calculate deflection of free end we have remembered, it is PL cube by 3I, and P by delta is stiffness, so stiffness will be 3I upon L cube. That's it. What you can do now, just reverse that and remove P, because P by delta, see delta by P is L cube by 3I, so P by delta will be reverse of this. So reverse this, remove P, you will get the expression of KB. Okay. But to write this expression, KB means I am replacing this entire structure with a spring, and we are considering bending stiffness of this, which is 3I upon L cube. Below this, I am attaching the mass. And after calculating KB, you can easily calculate natural frequency. It will be root over KB by M. Yes. But for that, you should know this formula. So what I am doing now, for various standard case, I am writing the formula of delta. If you know the formula of delta, you can easily write the expression of bending stiffness. And this you can do in your mind. Like suppose same question is coming in GATE examination. You have to write the expression of bending stiffness. How you can calculate? See, at this structure, rotor is attached the free end. So if in free end, if I will apply a concentrated load P, it is a cantilever beam, and in cantilever beam, if you are applying a transverse load P at free end, formula to calculate deflection of free end, this you can do in your mind, is PL cube by 3I. So stiffness will be 3I upon L cube. Reverse that and remove P. So bending stiffness of this structure is, here I am only writing the bending stiffness, 3I upon L cube. Now in this expression, what is E? It is Young modulus. What is I? I don't think I is mass inertia. Whenever we are writing the formula of deflection, in this deflection formula, area moment of inertia always comes into picture. So what is I? I is area moment of inertia of the cross section about neutral axis. Like suppose if just for one cross section I am writing the formula. If cross section is circular, whose diameter is D, okay, and neutral axis is nothing but centroidal x-axis of entire cross section is neutral axis. This thing you will study in strength of material. But for circular cross section, the formula to calculate I is, that is area and shape of neutral axis, is pi by 64 d to the power 4. Like if it is rectangular cross section whose width is h, height is h, the formula to calculate I about neutral axis is bh cube by 12. Okay, so this formula you will study in strength of material. Okay, yes. And sometime in vibration, examiner directly gives the product of P and I, which is flexure rigidity. Okay. Now what I am doing now, for various cases I am writing the formula of deflection, and after writing formula of deflection, you can easily write the formula of bending stiffness also. Like I am taking one by one. First of all, whenever in cantilever beam, if concentrated load P is applied at the free end, the formula to calculate deflection of the same point, flexure rigidity is EI, length is L, is PL cube by 3I. Because if you will know this formula, you can easily write the expression of bending stiffness. So first I am writing the formula of due to transverse load, concentrated transverse load in various cases. Okay. Now similarly, if in cantilever beam, concentrated load P is applied, but it is not applied at free end. So what we'll do now, suppose this distance is A, this distance is B, length of entire beam is L, flexure rigidity is A. Now my objective is to calculate the deflection of same point where load P is applied. So whatever formula I am writing now, I am writing the formula to calculate the deflection of same point where load P is applied. Because if I am calculating the deflection of the same point where load P is applied, then P by delta is bending stiffness. Okay. So see, in this case now, same formula is valued. See, in cantilever beam now, if only one concentrated load is acting. So, and if you want to calculate the deflection of that point now, just see the distance of that point from fixed end. Right now, since it is applied at free end, so entire length of the beam is coming, it is L. But distance of this point from fixed end is L, then formula of delta is PL cube by 3I. Why I am explaining this? Now here, if you want to write the expression of delta, means deflection of the point where load P is applied. See the distance of this point from fixed end, it is A. Then here the formula to calculate delta is PA cube by 3I. Just see the distance of this point where load is applied from fixed end. So this formula is for cantilever beam. Now similarly, some standard formula for simply supported beam. Simply supported beam means if in any beam, one end of the beam is hinged, this is hinge support, and other end roller support is provided. So this is known as simply supported beam. Simply supported beam. Now in simply supported beam, now if we are applying a concentrated load P at the center, this formula you will study in strength of material, but here we have to remember. Then the formula to calculate deflection of the same point where load P is applied, if it is applied at the center, is PL cube by 48 AI. This you have to remember. EI again is again flexure rigidity, na? Okay. Now I am writing this formula, but this formula should fit in your mind. Okay. Similarly, if in a simply supported beam, if load P is not applied at the center, suppose its distance from one support is A and its distance from other support is B, total length of the beam is L. Then the formula to calculate deflection of the same point where load P is applied is P A square B square, remember like this, A square B square upon 3 EI L. This is the formula. Here na, okay. Sometimes student do na, sometimes they write this as A cube B cube. No, it's A square B square, that you have to remember. Divide by 3IL. Okay. And here na, ultimately units should balance. Like suppose here if P is coming na, below side EI is coming, so here length cube is coming. Means with P upon EI you can see meter cube is multiplied. So this is P upon EI, it is common in all case. Now here if I written above side A square B square, so it is meter to the power 4. So that's why to balance the unit below side L is coming. So like this formula will fit in your mind. But this formula you have to remember. Now in this formula if you replace A by L by 2, B by L by 2, you will get same expression. Because this is the sub case of this part, na, where A and B is L by 2. Okay. Now similarly, this is standard formula for fixed beam. Fixed beam means if both end of the beam is fixed. Okay. Now in this fixed beam, if we are applying concentrated transverse load at the center, then formula to calculate deflection of the same point is PL cube by 192 EI. Okay. Now similarly, if in a fixed beam, this load P is not applied at the center. So suppose its distance from one support is A, other support is B, and distance between both the support is L. Then formula to calculate deflection of same point where load P is applied is P A cube B cube upon 3 EI L cube. See, here A square B square was coming, but here A cube B cube will come. Now A cube B cube means it is meter to the power 6, but we want meter cube. For that below side we are taking L cube. Now in this expression, if you put A equal to L by 2, B equal to L by 2, you will get automatically this expression. Okay. Now if you remember this formula, now you can easily write the expression of bending stiffness. Now I am writing the expression of bending stiffness for various cases. One by one. Na? Like in cantilever beam, if rotor is attached at the free end and transverse vibration is occurring, na, this I will not tell again and again. So here I am only writing the expression of bending stiffness. You can easily write. Simply see, in cantilever beam, rotor is attached at free end. Now do this calculation in your mind. So at free end, if I will apply concentrated load P, then formula to calculate deflection of free end is P L cube by 3I. So bending stiffness will be 3 EI upon L cube. Just reverse that and remove the load P, because P by delta is bending stiffness. Okay. Now easily you can calculate bending stiffness, then you can calculate omega n. Similarly, if it is a cantilever beam, but rotor is not attached at the free end. So see its distance from fixed end. Suppose this distance is A, this distance is B. Flexure rigidity is I. So what will be the expression of bending stiffness? So see, at the location where this mass is attached, if at this location I will apply transverse load, then what is the formula to calculate deflection of the same point? For that, see the distance of this point from fixed end, it is A. Then formula to calculate deflection is P A cube by 3I. And if deflection is P A cube by 3I, already written here, na? So bending stiffness will be reverse of that and remove P, that is it is 3 EI upon A cube. Yes. Okay. Similarly, in simply supported beam, if mass or rotor is attached at the center, so what will be the expression of bending stiffness? So see, in simply supported beam, if you will apply a concentrated load at the center, then formula to calculate deflection of same point is P L cube by 48 EI. So bending stiffness will be 48 EI upon L cube, because it is P by delta. Okay. Similarly, in simply supported beam, if rotor is not attached at the center, distance from one support is suppose A, from other support it is B, distance between both the support is L. So now what will happen, if we will apply concentrated load at this point, suppose P, then deflection of the same point will be P A square B square upon 3 EI L. So bending stiffness will be 3 EI L upon A square B square. Very easy. Clear? Yes. Similarly, in fixed beam, if rotor or point mass is attached at the center, then what will be the expression of bending stiffness? So at the point where this rotor or point mass is attached, at this point if you apply a transverse load P, then the formula to calculate deflection of same point is P L cube by 192 EI. So bending stiffness will be 192 EI upon L cube. Easy. Similarly, in fixed beam, if rotor is not at the center, so its distance from one support is A, from other support is B, and distance between both the support is L. So what will be the expression of bending stiffness? So see, at this point, if I will apply a transverse load P, then what is the formula to calculate deflection of same point? For fixed beam, this formula is P A cube B cube upon 3 EI L cube. So bending stiffness will be reverse of that and remove the P. So 3 EI L cube upon A cube B cube. So this is the expression to calculate bending stiffness. Clear? Okay. Like we are discussing one question based on this formula. Then I will discuss some special case also in this case, in transverse vibration case. First I am discussing this question. What this question is saying? A beam of length 2 meter is simply supported at the end, it is simply supported beam, is carrying a point mass of 100 kg at a distance 0.5 meter from one end. Flexure rigidity of the beam is 80,000 Newton meter square. So directly the product of E and I is given, and it is given in SI unit. Then exam asking natural frequency of transverse vibration in radian per second. So see, it is a simply supported beam. Now even now, it's always should be mentioned whether we have to calculate natural frequency of transverse vibration, longitudinal vibration. But even if it is not mentioned now, it is suppose question is saying calculate natural frequency. That's it. Then also by you reading this question, you can tell examiner want to ask natural frequency of transverse vibration. That's why flexure rigidity is given in the question. So if it is not mentioned, then also by observation you can tell examiner wants natural frequency of transverse vibration. Okay. So it is a simply supported beam whose length is 2 meter. Use SI unit na L. Now rotor or mass M is attached and the value of M is 100 kg. It is attached at a distance 0.5 meter from one support. So this is suppose 0.5. So it will be 2 minus 0.5 means 1.5 meter. Flexure rigidity of this structure EI is 80,000 Newton meter square. Then we have to calculate natural frequency in radian per second, that is omega. Now here transverse vibration is occurring. So first we will calculate bending stiffness of this beam. Suppose that I am denoting as KB. What will be this expression? So see, it is a simply supported beam in which rotor is not attached at the center. So if at this point, if I will apply a transverse load, what is the formula to calculate deflection of the same point? If load is P, the formula to calculate deflection of same point is P A square B square upon 3 EIL. So bending stiffness will be 3 EIL upon A square B square, where EI is flexure rigidity, L is total length of the beam. What is A and B? Distance of this rotor from one support is A and other distance is B. Now just put the value. 3 EI is directly given, it is 80,000 into L is 2 meter upon A square. Suppose this distance I am considering as A, it is 0.5 meter, so square. Then this distance 1.5 will be B, so into 1.5 square. It's if you are taking SI unit, bending stiffness unit will be Newton per meter, because ultimately it is force per unit deflection. Na? So SI unit of force is Newton, SI unit of deflection is meter. So unit of bending stiffness will be Newton per meter. How much it is coming? 380,000 into 2 divided by 0.5 square into 1.5 square. You can check. Is it coming 853333.3333 Newton per meter? You can check the calculation. Yes. Now after calculating KB, now we can calculate natural frequency of transverse vibration radian per second. It will be square root of KB upon the value of point mass M. Now KB is 853333.3333 upon the value of mass m in kg, it is 100 kg. So how much omega n is coming? It is coming 92.376. Yes, radian per second. And exam asking natural frequency in radian per second. So the answer is 92.376. So for this question, natural frequency is 92.376. Exam asking round up to 2 decimal place. So if you round up 92.376, mathematically up to 2 decimal place, it will be 92.38. So this is correct answer for this question. Okay. Now next question. This is very good question. We have to find the expression of natural frequency in radian per second. Here spring is also attached. Na? See, whenever this type of question is coming, na, I will suggest draw the equivalent diagram first. How? See. First of all, na, this spring is attached, good. But in this structure, I am 100% sure transverse vibration will occur. How? See, if this mass will vibrate like this, and when it will vibrate, spring will vibrate like this. But this point of the structure will move like this. And if it is moving like this beam will bend. So here bending stiffness will come into picture, means in this beam transverse vibration will occur. Now what will happen now? If this type of problem is coming, we'll always draw equivalent diagram. Equivalent diagram means, see, this spring is directly attached to the mass. So here now I can use series parallel arrangement. But here the problem is now this beam, because directly in question the stiffness of this beam is not given. So what I need to do? First I need to find the stiffness of this structure. Okay, so what I will do now, instead of calculating equivalent stiffness of entire structure, first we will calculate stiffness of this part. Again repeating, what we'll do now in this type of case, the spring which are directly attached to the mass. Right now don't consider those springs. Apart from this spring, consider the other system. So other system is this part. So what we'll do now, instead of calculating equivalent stiffness of entire structure, first we'll calculate equivalent stiffness of this part. Suppose equivalent stiffness of this part is Ke dash. But equivalent stiffness of this part is nothing but it is the bending stiffness of this structure. Why? Because you can see in this structure only beam is coming, in which transverse vibration is occurring. And if transverse vibration is occurring, the bending stiffness will come into picture. And how you can write the bending stiffness expression of this structure? Okay, you can directly write, but for understanding I am drawing the diagram. See, if your objective, I am writing separately by making a box. If your objective is only to calculate Ke dash, which is nothing but Kb. Okay, Ke dash or Kb means if stiffness of this part. Just 1 second. So what we'll do now, right now our focus is on the calculation of stiffness of this part only. So if you want to calculate stiffness of this part also only now, so right now I will suggest don't consider this spring, because right now I am not calculating overall K equivalent. And just imagine if this spring is not present in this system. So can I say in that case this mass will be present here. Mass will be here. So just remove this spring which are directly connected to the mass. And if you are removing that spring, where mass will be attached? It will be attached here. Yeah. Okay. Now calculate the bending stiffness of this portion, because here only beam is coming, and in this beam transverse vibration is occurring. So how, and whatever bending stiffness is coming, that is also Ke dash. So how you can write this expression? So it is a cantilever beam in which rotor is attached at the free end. So at this free end, if you will apply a transverse load P, what is the formula to calculate deflection? It is P L cube by 3I. So what will be the expression of bending stiffness? It will be 3I upon L cube. Very simple. And after that, just draw the equivalent diagram. How you can draw the equivalent diagram? Okay, this is not the equivalent stiffness of entire structure. It is the equivalent stiffness only this portion, which is the bending stiffness of this beam. And after that, draw the equivalent diagram. Equivalent diagram means we will replace this portion by single spring. whose stiffness is either KE dash or KB. Now we have calculated the expression of KB. It is 3I upon L cube. Now consider those system which we have left earlier. Means we have left this spring. Now consider this spring also. So now actually here mass is not attached. Now below this spring is attached whose stiffness is K. And below this mass is attached. So now by using series parallel arrangement, first draw this equivalent diagram. And after that by using series parallel arrangement, you can calculate overall K equivalent. But to use series parallel arrangement, first draw this equivalent diagram. Okay. Now you can easily calculate K equivalent. But here most important was the calculation of KB. Okay. But for KB calculation, you need not to draw this diagram separately. This I explained only for understanding. This you can do in your mind. See. Very simple. If this is spring, because we have to calculate bending stiffness of this structure first. Na? So if this spring are not there, this mass M will be here, which is means this mass M will be at free end of cantilever beam. Now at free end of cantilever beam, if transverse load P is acting, the formula to calculate delta is PLQ by 3I. So bending stiffness will be 3I upon L cube. Very easy. So KB dash you can easily write KB. It will be 3I upon L cube. Now after that draw equivalent diagram. We are replacing this with the spring whose stiffness is KB. Now below this spring is attached whose stiffness is K. Below this mass is attached. Now use series parallel arrangement. Now can I say 1 and 2 are in series? So here now 1 and 2 are in series. So we can calculate overall K equivalent. They are in series means having end-to-end connection. And in end-to-end connection to you calculate K equivalent will use reciprocal formula. So suppose their equivalent stiffness is K, which is overall K equivalent. So 1 upon K will be equal to 1 upon K1, which is KB, plus 1 upon K2, which is K. It is given in the question. Na? Yes. Now 1 upon K equal to 1 upon KB. KB is 3EI upon L cube. L cube will go below above side plus 1 upon K. So 1 upon K equal to 3I and K LCM is 3EIK. 3IK divided by this is K. Now K into L cube is KL cube plus 3IK upon K is 3I. 3I into 1 is 3I. So what is the expression of K equivalent? It is 3EIK upon KL cube plus 3I. Now after calculating K equivalent, now we can calculate omega. It will be square root of K upon the value of mass M, and K is 3EIK upon KL cube plus 3EI into M. Clear? So like this you can do calculation. I am discussing with one more question. Here in this question, we have to calculate time period of natural vibration in second. For that, again, first we'll calculate omega n. Na? And for omega n, first we need to calculate overall K equivalent. Okay. Now how? See, these spring are directly attached to the mass. Na? So right now, don't bother about the spring. First of all, apart from this spring, whatever system is coming here, this system in which beam is coming, first calculate the equivalent stiffness of this system, that is KE dash. Now you can see in this diagram, which we have covered in this loop, only beam is coming. And in this beam, transverse vibration will occur. Why transverse vibration will occur? Because when mass will vibrate like this point will move up and down. Up and down means this beam will deflect in transverse direction. So since in this structure which I covered in this loop, transverse vibration is occurring. So KE dash is nothing but it is bending stiffness of this beam. Okay. Now for this KB calculation or KE dash calculation, you need not to draw separate diagram. If you want, you can draw. But you can do this in calculation in mind. Just imagine if this spring are not present in the system, we'll attach this mass here. We'll attach this mass here. Mass here means it is attached in the center of simply support. Oh, okay. This is typing error. Actually, this is attached. It should be given. This distance is L by 2. This was typing error. Na? Okay. So if this spring are not attached in the system, this mass M will be here, which is the center of this simply supported beam. Now, whenever in simply supported beam, if rotor is attached the center, what will be the expression of bending stiffness? So, if in the center of simply supported beam, if I will apply a transverse load P, then the formula to calculate deflection of same point is PL cube by 48 EI. And if delta is PL cube by 40 EI, stiffness will be 48 EI upon L cube. Here the bending stiffness of this beam is 48 EI upon L cube, where EI is flexure rigidity of this beam. It will be given in the question. Don't worry. So 48 EI upon L cube. So we have calculated KB. Now after that, draw equivalent diagram. Now how you can draw the equivalent diagram? I am replacing this portion of the structure with single spring, whose stiffness is KB, and KB we have calculated 48 EI upon L cube. Now consider the other spring. Now with this structure, first this spring is attached, whose stiffness is 24 EI upon L cube. Yes. Now below this mass is attached. Yes. And below this, now this spring is attached, whose stiffness is 24 EI upon L cube. Now from this equivalent diagram, we will calculate overall K equivalent. For that, suppose this I am considering as 1, this as 2, this as 3. Now how you can calculate overall K equivalent? So see, whenever mass is attached the middle, we know the equivalent stiffness of this side portion and equivalent stiffness of this side portion will be in parallel arrangement. Now we already know equivalent stiffness of this side portion, but this side portion 2 spring is coming. So first calculate equivalent stiffness of this side portion. And in this side portion, 1 and 2 are making end-to-end connection. So can I say they are in series? So by using series formula, we can calculate their equivalent. And since I am referring this as 1, this as 2, so their equivalent will be K12. So first I am calculating K12. And how we can calculate K12? Since 1 and 2 are in series, since 1 and 2 are in series, their equivalent, that is K12, will be 1 upon K12 equal to 1 upon K1. K1 is nothing but KB, which is 48 EI upon L cube, plus 1 upon K2. K2 is this stiffness, which is 24 EI upon L cube. So 1 upon K12 equal to, now sum of 48 and 24 is 48. So it is 48 EI. 48 EI divided by 48 is 1 into L cube is L cube, plus 48 by 24 is 2. So it is 2 L cube. 2 plus 1, it is coming 3 L cube by 48 EI. You can check the calculation. 3 1 ja 3. 3 1 ja 1, 3 6 ja. So it is coming L cube by 16 EI. You can check the calculation. Na? Calculation is your part. So K12 will be 16 EI upon L cube. Okay. So this is K12. Now we know equivalent stiffness of this side system, which is K12, and this side system, which is K3, are in parallel arrangement. And in parallel arrangement, to calculate equivalent, we add the stiffness of individual spring. So now I can calculate overall K equivalent because K12 and 3 are in parallel. Now if I will calculate their equivalent, that will be overall K equivalent, because after that no other spring are left. And since they are in parallel, overall K equivalent will be K12 plus K3. K12 is this, which is 16 EI upon L cube. And when I am saying K3, K3 means stiffness of this spring, which is 24 EI upon L cube. So it will be 24 plus 16. Calculation is your part now. Just add them. 24 plus 16. It is coming 40 EI upon L cube. So this is overall K equivalent. And after calculating overall K equivalent, now we can calculate natural frequency of transverse vibration, that is omega n in radian per second. It will be root over K equivalent upon the value of mass m. K equivalent is 48 EI upon L cube and mass m is m. Okay. So it is in radian per second. Now examiner asking time period. So if the natural frequency radian per second is omega n, time period will be 2 pi by omega n. So 2 pi by omega n. Omega n is coming below side, means just reverse this. So it will be root over ml cube upon 48. Second. So this is the expression of time period of natural vibration. Clear? Yes. So we had discussed the concept of transverse vibration also. Now we'll discuss torsional vibration. Just 1 second. See, now we are discussing torsional vibration. See, if you understood longitudinal vibration, you will easily understood torsional vibration also, because what I will do now, I will relate torsional vibration with longitudinal vibration with some analogy. So it will be easy for you to solve the questions. Okay, just I am taking one case. Suppose this is a shaft. Now it is your will, you can refer this as shaft, beam or bar, but generally when torsional vibration occurs, now we refer the structure as shaft. Okay, here one rotor is attached. Okay, shaft is right now massless. Now length of the shaft is L and the torsional rigidity of the shaft is GJ. Like in longitudinal vibration, axial rigidity comes into picture, which is A. Transverse vibration, flexure rigidity comes into picture, which is EI. Similarly, in torsional vibration, the torsional rigidity will comes into picture. How you will understand? Which is GJ, where G is nothing but it is the shear modulus or modulus of rigidity of the shaft material. It will be given in the question. Okay. And what is J? J is polar area moment of inertia of cross section. In rigidity formula, whatever this, whether I is coming, whether J is coming, that is not mass moment of inertia, it is area moment of inertia. And in torsion case, polar area moment of inertia comes into picture. Polar area moment of inertia means if the suppose cross section is circular, whose diameter is D. So what is J na? It is the polar area moment of inertia of the cross section about centroid. Whenever I am saying polar area moment of inertia, means it is the area moment of inertia of the cross section about perpendicular axis of the cross section. Suppose the perpendicular cross axis of the cross section is Z. So it is polar area moment of inertia about centroidal Z axis. But whenever I am using polar word, means it is by default, it is the area moment of inertia about perpendicular axis, which is passing through centroid. Now what is the formula? Just remember the formula. If the cross section is circular, the formula to calculate polar inertia is pi by 32 d to the power 4. The formula to calculate area moment of inertia about neutral axis, try to recall, in circular cross section was pi by 64 d to the power 4. But for circular cross section, the formula to calculate polar area moment of inertia is pi by 32 d to the power 4. Okay. Similarly, you can remember for other cross section also. I am writing only for circular. And here GJ is known as torsion rigidity. Okay. See, first of all, now in this rotor, what I am doing, I am disturbing the rotor by rotating about longitudinal axis like this. Okay. Due to that, what will happen at this point of the shaft, twist will create. And since twist is creating, here torsional stiffness of this shaft will come into picture. Now, whatever torque I apply to disturb this rotor, suppose if I will remove that load. So what will happen now? Due to that torsional stiffness, this shaft will try to come to its mean position. But at when it will reach to its mean position, it will have some angular velocity. Due to that, it will go in other side and it will vibrate like this. And since this vibration is occurring about longitudinal axis, this vibration is known as torsional vibration. And in torsional vibration, torsional stiffness of the shaft is responsible for restoration. So here, can I say, if you want to calculate natural frequency, first of all, most important calculation is the calculation of torsional stiffness. Yes. Now, how you can find the expression of torsional stiffness? Suppose that I am denoting as KT. Okay. So like now, to calculate axial stiffness, what we were doing at the location where rotor was attached, we are applying a concentrated load in longitudinal direction. Suppose that load was P. Then we are calculating the deflection of same point in longitudinal direction. Suppose that was delta. So P by delta was axial stiffness. Same thing we were doing for bending stiffness calculation also. Only difference, we were applying the load in transverse direction. Similarly, if I want to calculate the expression of torsional stiffness, Can I say at this point where rotor is attached, I will apply a concentrated load about the longitudinal axis. Why about longitudinal axis? Because here vibration is occurring about longitudinal axis. And when you will apply concentrated load about longitudinal axis, we need to apply a torque because here rotation is occurring. So about longitudinal axis, if you are applying a load, how you can apply a force? About this, we'll apply a torque. So here what we'll do at the location where rotor is attached, at that location to calculate torsion stiffness, we'll apply a concentrated torque instead of concentrated load, force. Okay. Now due to this torque, since it is a torque, we'll calculate the angle of twist of the same point. Like we were calculating the deflection in axial direction in case of longitudinal vibration. Similarly, here we'll calculate the deflection in about longitudinal axis, and about longitudinal axis rotation is occurring. That's why we'll calculate the angle of twist of the same point. Suppose that is theta A. Then this T by theta A is nothing but torsional stiffness of this shaft KT. Okay. And its SI unit is not Newton per meter. Its SI unit will be, SI unit of torque is Newton meter per theta. SI unit of theta is radian. So its unit is Newton meter per radian. Now what will be its expression? Now if you see, you have studied this formula in strength of material. If you want to calculate theta A, again calculate theta A with respect to this point because B is fixed, theta AB. Okay. Now, like in bar, if axial force is acting is P, area is A, young modulus is E. So we know due to axial load, the formula to calculate deflection of any portion of bar is PL upon AE if the axial force, area and E of each cross section of bar is same. Similarly, in case of shaft, a torsional load is acting. So if the torsional rigidity of any portion is like same, like right now torsional rigidity of each cross section of AB is same, which is GJ. And if torsion moment resistance is same, right now it is same for poor entire AB portion, which is T. Then formula to calculate angle of twist of that portion is TL upon GJ. Means instead of P, torsion moment T is coming, and instead of axial rigidity, that is AE, torsion rigidity GJ is coming into picture. So here the formula to calculate theta AB is TL upon GJ. And since B is fixed, it is also total theta A. So from this, if you will calculate T by theta A, can I say it will be GJ by L? So like in bar, axial stiffness was AE by L. Here instead of AE, GJ is coming into picture, means torsion rigidity. So formula to calculate torsion stiffness if one end of the shaft is fixed, at other end rotor is attached. So now you can directly remember the formula to calculate torsion stiffness is GJ by L. So first of all, this is about stiffness. Now you will remember this formula. The formula to calculate torsion stiffness of this shaft is GJ by L, where G is modulus of rigidity. J is not mass unit inertia, it is polar area unit of the cross section. If it is circular, the formula to calculate J is pi by 32 d to the power 4 and L is the length of the shaft. Okay. See, now we know the formula to calculate natural frequency is, in case of longitudinal vibration, it was root over K by M. So can I say here instead of K, KT will come, which is the torsion stiffness. But here one more difference will come. Here instead of mass, okay, mass means it is the inertia of this rotor. Instead of mass, because this mass is not vibrating with linear motion. This mass is vibrating with rotational motion. So here instead of mass of the rotor, mass moment of inertia of the rotor will come into picture. It is mass of inertia, it is not area. Because whenever in this formula I am writing the term which is coming below side. So here we take the inertia of the object. Inertia means by including mass. So in case of translation motion, the mass of that body was coming. Okay. But in case of rotational vibration, mass moment of inertia of this rotor will come into picture. So suppose the mass inertia of this rotor about axis of rotation is I or I naught. But don't think this I is this I which we have studied in bending formula. No, this I was area moment of inertia about neutral axis. Okay, and here below set point mass was M is was coming. But here this I or I naught is mass inertia of this rotor about axis of rotation. Because here rotational vibration is occurring. So the formula to calculate omega and in case of transverse vibration will be root over KT, where KT is torsion stiffness. okay, upon instead of mass inertia of the rotor, which is I naught. It is mass inertia. So clearly right now it is mass inertia of rotor. Mass inertia of rotor about axis of rotation. So omega n will be root over kT by I naught. Now I am just drawing the equivalent diagram. You can easily relate this. See, we have to calculate natural frequency of torsional vibration. Suppose this is the shaft whose torsal rigidity is GJ, length is L, and mass inertia of the rotor is I naught. Whenever I am writing I naught, it is the mass inertia of rotor about axis rotation. I will not write again and again. And if you want to calculate natural frequency of torsional vibration, I will suggest draw equivalent diagram. Okay. Now when we are drawing equivalent diagram now, I am comparing this with longitudinal vibration. Only difference is instead of axial stiffness, torsional stiffness will come into picture, and instead of mass of the rotor, mass inertia of the rotor will come into picture. But when we are drawing equivalent diagram, now just draw like longitudinal vibration, because you can compare with longitudinal vibration. Only difference, instead of axial stiffness, torsional stiffness, instead of mass inertia of the rotor is coming into picture. So what we will do now? Right now, the torsal rigidity of entire shaft is same. So suppose this shaft is 1. So what we'll do? We'll replace shaft 1 with spring 1, whose torsal stiffness is KT1. I am showing like linear diagram, but actually we'll write the torsal stiffness. Okay. Actually, it is torsal stiffness. But in equivalent diagram, I am showing as linear diagram, because it will be easy for you to do the analysis. So torsal stiffness is KT1. It will be torsal rigidity GJ upon length of the shaft is L. Now below this rotor is attached. So I am showing like a mass, but actually here instead of mass we'll write mass inertia. Just remember the analogy. Okay. So now what will be natural frequency of torsal vibration, that is omega, and it will be root over KT1 upon I naught. KT1 in numerical you can calculate separately. Right now the expression of KT1 is GJ by L. So GJ by L divided by I naught. Clear? Now what is the benefit of this? If diagram is coming like this, now you can easily calculate overall KT equivalent. Suppose the torsal rigidity of this portion is 2 GJ, length is L. Below it this shaft is attached, whose torsal rigidity is GJ, length is L. Okay. And here suppose rotor is attached, whose mass inertia about axial rotation is I naught, and we want to calculate natural frequency of torsal vibration. Why mass inertia is coming instead of mass? That is your question, Santosh. Because here rotational vibration is occurring. See what will happen now. Just for to clear your doubt now. Okay. But remember this summary. Just to clear your doubt now, I am doing the proper derivation. Suppose I am using energy method. I am hoping in YouTube you have watched the class of rotational vibration, because in earlier class I told in YouTube in this channel I had discussed rotational vibration, in which I had discussed energy method to derive the equation of vibration. I am hoping you have studied that lecture. So see here rotor is attached. Suppose whose mass inertia is I naught. See. Now suppose to derive the equation of vibration, I am taking any position in which this rotor has rotated by theta angle from its mean position. Suppose theta I am taking anti-clockwise. I am drawing the side view. And if it is rotated by theta angle, angular velocity will be theta dot, angular acceleration will be theta double dot. Okay. Now if you are using energy method to derive the equation of vibration, in energy method what we do? We find the expression of kinetic energy. We find the expression of potential energy. Then we add them, that is the expression of total energy. And we know in natural vibration total energy is constant, because in natural vibration energy loss doesn't occur. And if total energy is constant, so it will differentiate with respect to time, and then it will be 0. Why? If total energy is constant, means its differentiation with respect to time will be 0. So what we'll do, we'll find the expression of kinetic energy, potential energy, we'll add them, that is total energy, differentiate with respect to time, equate with 0, you will automatically get the equation of vibration. Now kinetic energy comes due to that part whose inertia is given. So right now inertia of rotor is given. Now what is the formula to calculate kinetic energy? If any body is translating, then formula to calculate kinetic energy is half mv square, where m is the mass and v is linear velocity. But if any body is rotating, here the difference is coming, Santosh. Then formula to calculate kinetic energy is not half mv square, it is half I omega square, where I is mass inertia about axis of rotation and omega is angular velocity. So since rotor is rotating, shaft is massless, na? That's why I'm calculating kinetic energy only for rotor. So that's why kinetic energy will be half I naught, which is mass inertia about axis of rotation, into omega square. Now angular displacement of the rotor is theta, so angular velocity will be theta dot. So it is theta dot square. Due to this reason I naught is coming. Now what about potential energy? Potential energy will come due to stiffness. Now for linear spring, formula to calculate potential energy is half kx square, where k is the stiffness of spring and x is displacement, linear displacement from mean position. Similarly, if in case of torsional spring, because now this shaft is twisting, so its stiffness is torsional stiffness. So you can refer this shaft as torsional spring. The formula to calculate potential energy is half kt theta square. Instead of k, kt, instead of x, theta, where kt is the torsional stiffness and theta is angle of twist. Okay, so half kt theta square. Now just add them, differentiate with respect to time and equate with 0. So d by dt kinetic energy is half I naught theta dot square plus potential energy is half kt theta square and equate with 0. Now half I naught. Now differentiation of theta dot square with respect to time. So I will use chain rule. First differentiate theta dot square with respect to theta dot, it will be 2 theta dot. Now differentiate theta dot with respect to time, it is theta double dot plus half kt theta square. Differentiation of theta square with respect to theta is 2 theta. Now differentiation of theta with respect to time is theta dot, equate with 0. Now bring the common term outside, it will come this side, it will become 0. So half is coming directly common. This 2 theta dot and here 2 theta dot is coming common. Common part will come this side, it will become 0. So equation is coming I naught theta double dot plus kt theta. It is in general form. Like for spring mass system na, equation was mx double dot plus kx was 0. So omega 1 was root k by m. So here instead of k, kt is coming, instead of m, I naught is coming, because the coefficient of theta is kt, coefficient of theta double dot is I naught. So omega n will be root over kt by I naught. Okay, but there is no benefit of this derivation. Just remember this analogy. Draw this equivalent diagram. Only remember, replace this by spring. I am drawing line linear, but it is the torsion spring stiffness, which will be Gj by L. Below this rotor is attached. So draw like I am drawing like linear vibration, but actually rotational vibration is occurring na. So instead of mass units of the rotor will come into picture. Okay, and what is the benefit of drawing this equivalent diagram? Even if Gj will change suddenly, you will be able to calculate overall KT equivalent. How? Now solve this. Just 1 second na. See, suppose this is shaft 1, shaft 2. So I will replace shaft 1 by spring 1. Now write the torsion stiffness, that is KT1. It will be torsion rigidity 2Gj upon length is L. Now below, beside this shaft 2 is attached, whose stiffness is KT2. It will be torsion rigidity Gj upon length L. Below this rotor is attached, beside this. Now rotor. Now instead of mass, write the mass units of the rotor about axis rotation, which is I naught. Okay. Now suppose this is 1, this is 2. It is having end-to-end connection, so they will be in series arrangement. So now I can calculate their equivalent, and their equivalent will be overall KT equivalent, because apart from this no other spring is coming. Okay, so 1 upon KT equivalent, because in series we use reciprocal formula. It will be equal to 1 upon KT1. KT1 is 2Gj upon L plus 1 upon KT2, and KT2 is Gj upon L will go above. So 1 upon KT equivalent will be equal to L upon Gj will come common na. So it is coming 1 by 2 plus 1. It will be 2 plus 1, 3 by 2 L by Gj. So KT equivalent will be 2GJ by 3L. Now after calculating KT equivalent, now we can calculate omega n. It will be root over KT equivalent upon I naught. KT equivalent is 2GJ by 3L divided by. So this is the answer. Clear? Like this is last question. I am solving this question. In this question, you have to find the expression of natural frequency of transverse vibration. Here I am discussing the solution. Now what we'll do? Suppose this is shaft 1. Its torsionality is different. This is shaft 2. Now this shaft I will always consider separate because rotor is attached at the middle. Na? So this side portion and this side portion will always consider separately. So sir, suppose this is shaft 3. Okay. Now I will draw this equivalent diagram. So we will replace this shaft 1 by spring 1 whose torsion stiffness is KT1 and it will be torsion rigidity is 2JJ upon length of shaft 1 is L. So it will be 2GJ upon L. Now beside this shaft 2 is attached, which I am replacing with spring 2 whose torsion stiffness is KT2. It will be torsion rigidity is GJ upon length is L. So it is GJ by L. Now after that this rotor is attached. So now apply rotor. But here instead of mass we will write mass inertia of the rotor about axis of rotation, which in question is represented as I. That's why I am represented as I. Because in question it is given na mass inertia is I. Now after that this shaft is attached, so replaced by spring 3 whose torsion stiffness is KT3 and it will be torsion rigidity GJ upon length L. Okay. Now after this we have to calculate overall KT equivalent. How you can calculate? Suppose this is 1, this is 2, this is 3. Now we know whenever rotor is attached the middle, this side system equivalent and this side system equivalent will be in parallel arrangement. Okay. Now in this side only one spring is coming, so we know the equivalent stiffness of this side. But this side multiple spring is coming now. So first calculate equivalent stiffness of this side system. Now in this side system 2 spring is coming 1 and 2. So suppose their equivalent stiffness is K12 and how we can calculate K12? So this 1 and 2 are having end-to-end connection. End-to-end connection means can I say 1 and 2 are in series. So by using series formula we can calculate KT12. T for torsion stiffness. So suppose their stiffness I am representing as KT12. So how we can calculate KT12? Just 1 second. So since 1 and 2 are in series, we will use reciprocal formula. So 1 upon KT12 will be equal to 1 upon KT1. KT1 is 2GJ upon L plus 1 upon KT2 and KT2 is GJ upon L. So 1 upon KT12, you can do calculation, it's your partner. L upon GJ is common. So 1 by 2 plus 1. It will be 3 by 2. So it is coming 3L by 2GJ. So KT12 will be 2GJ upon 3L. Clear? Yes. Now, equivalent stiffness of this side system, that is KT12, and equivalent stiffness of this side, which is KT3, are in parallel arrangement. So now we can calculate overall equivalent, that is overall KT equivalent. How? So see, now we know KT12 and KT3, they are in parallel. And in parallel arrangement, to calculate equivalent stiffness, we add the stiffness of individual part. And their equivalent means overall KT equivalent, because after that no other spring are left. So overall KT equivalent will be equal to KT12 plus KT3. Now KT12 is 2GJ upon 3L plus KT3 is GJ upon L. So GJ upon L is, you can take common na. So it will be 2 by 3 plus 1, that is 5 by 3. Yes. So overall KT equivalent is coming 5 GJ by 3L. Yes. So now natural frequency in radian per second will be root over KT equivalent upon, instead of mass inertia of the rotor, which is I, and root over KT equivalent is 5 GJ by 3L upon I. Okay. So this is answer for this question. Clear? So that's all. Today we have completed longitudinal vibration, transverse vibration, and torsional vibration of single degree of freedom system. Okay. So we have completed single degree of freedom vibration part. In tomorrow lecture, I will discuss double degree of freedom vibration, and in last lecture, I will discuss continuous vibration. In continuous vibration, mainly we'll discuss longitudinal, transverse, and torsional vibration of infinite degree of freedom system. Okay, but that I will discuss in the last class. Okay, so that's all for today. I think it is clear to everyone. Okay, so ending the class now.